All right, good morning. Reaction video number 19. Here we go. Apparently constant acceleration equations. So let's see how it goes.
In this video, we're going to learn about 4 of the most important equations we'll learn all year. These are 4 equations that work when you have a constant acceleration, and you'll find them on your equation sheet. We'll start out with the first equation. The first equation tells us that the final velocity is equal to the initial velocity plus the acceleration times the time. Notice that I have vector symbols on top of the quantities that are vectors.
Yeah, I like those vector symbols. Easier than
bold. The second
bold.
equation tells us that the displacement is equal to 1/2 of the quantity, the initial velocity plus the final velocity times time.
Cool.
Our third equation says that displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. And our final equation says that the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times displacement.
So cool. So, often this is written a little bit differently, where this will have an x final and an x initial over here. I'm pausing because I'm actually wondering if this is true as a vector statement. Let me think. Is that true as a vector statement? Sorry, my brain's not working right now. Let's think. If you were to go, if the acceleration were perpendicular, let's say, you'd have that plus, I'm not used to seeing this as a vector statement. I mean, I really like how she's using vector symbols over all of these. Vector symbols instead of bold, right? Which is what so many textbook uses because students can't write in bold. So I'll have to really think about whether this is true as a vector statement. Certainly true as in one dimensions. No problem there, as long as acceleration is constant, which is what this whole equation is about. And this one, of course, it's confusing, right? Because the vector can't be squared, but the quantity can be. So it'll be curious to see how she deals with examples of these, although I don't know if she's going to get to examples of this one. And of course, you guys have heard me say this before, that I like that, this is a precursor. This is an energy equation. Multiply this by 1/2 m everywhere. You're like, oh, that's just work, right? Kinetic energy final, kinetic energy initial, and work. And so if you can get to this with some substantial monkeying around with these, you can get here, and it's so cool then when you get to kinetic energy and that kind of stuff. You're like, you guys, we've seen this before. You didn't realize it, and that's why it's true. That kind of stuff. So very cool. I love the handwriting. It was funny that she stepped away from the mic for a second, but I could hear her and came back again, so no problems there. So I'm curious to see what types of sort of derivations or examples she's going to be up to here.
So these are the 4 equations. They're very important to us in physics. To help us use these 4 equations, it's important to recognize what each equation is missing. What do I mean by that? Well, there's 5 variables that we could potentially have. We have displacement, initial velocity, final velocity, acceleration, and time.
That's really cool, right? Because you could describe it as 6, right? So instead of talking about displacement, you could talk about initial position and final position the same way you talk about with velocity. And so I think it's really, really interesting to talk about which ones we're considering as differences. And notice that x keeps showing up with this big old delta in front of it, right? So that's very cool. I've been thinking a little bit more about this equation while she was talking here. So if you think about this in 2 dimensions, right? So the x displacement would certainly be this, where this would be like the x acceleration. And then the y displacement would be this with y and this with the y. And so yeah, actually this is a vector equation. Similarly, I'm pretty sure this is a true vector equation. It's so funny that I've just never really worked problems that way, right? I usually just break it up. We're going to do the horizontal, then we're going to do the vertical. But you guys are going to laugh at me if I'm wrong, but I'm pretty sure that all 3 of these are vector equations.
But each of these 4 equations only has 4 variables. That means it's missing one.
Oh, I like that. 5
That'll
to 4.
help us choose which equation is best to use in each situation.
Yeah. What
So
do you
let's
know?
look
What do you need?
and see what variable each equation is missing. Our first equation is missing displacement.
Oh, that's cool to talk about what's
Our
missing.
second is missing acceleration. Our third is missing final velocity. And our fourth is missing time.
Man, that's really cool.
We'll refer back to these equations as we try our first problem,
Oh, exciting.
which is example number 8, on page 53, number 29 in your textbook. It says that a truck covers 40 meters in 8.5 seconds, while smoothly slowing down to a final speed of 2.8 meters per second. We're trying to find the truck's original speed, as well as the magnitude of its acceleration.
All right, so let's make some guesses here. So 2.8 meters per second is like, I don't know, 8 miles an hour. So we're really slowing down here. We're really going slow. And 40 meters is like a little bump off on a, like if you're pulling to a stop and a little bump, there's on the street outside, there's this little bump out. I think that's probably in the vicinity of 40 meters. 8.5 seconds is actually quite a while. Wow. 8.5 seconds to go 40 meters. It's not going that fast. What if it was 8? It would take 5, it'd be 5 meters per second. So yeah, maybe 7, 8 meters per second at the beginning here. And this is not like slamming on the brakes. So this is 1/10 of a G at most, I'm going to guess.
In this case, when it says to find the truck's original speed, we are looking for the magnitude of the truck's velocity. Let's start out by writing down what we're given.
Cool.
Well, we know that the displacement is equal to 40 meters.
Cool.
I'm going to leave that vector symbol off since I don't really know anything about direction.
Love that.
We know that the time that it takes to travel that distance is 8.5 seconds. We know that its final speed, and again, this time we're talking about really the magnitude of its final velocity, is 2.8 meters per second.
Cool.
In part A, we are looking for the initial speed, or again, the magnitude of the initial velocity. Let's look at the symbols that I've written on the board here. I've written 4 out of my 5 variables.
Right.
Which one am I missing?
So she's missing acceleration.
If you said that I'm missing acceleration, you are absolutely correct.
Woo!
So let's take a look at our
That's
equations.
cool. So you go back and you say which one doesn't have acceleration.
The equation
like,
that's
this one
missing
does-
acceleration
very cool.
is the second equation
Very
shown
cool,
here.
very cool.
So that's the equation we'll use for this problem.
So I really like how she's talking about what's missing as opposed to what's there, right? So often students will say, okay, we'll find an equation that has what you got, right? And if you look at her equations, there's lots of them that have bits and pieces, but she sort of flipped it. She said, look, for part A, we have all of this crap, but we don't have acceleration. We're not being asked for acceleration, right? It's not the question mark. So let's just find an equation that doesn't even have it at all, because apparently we can do part A without it. It'll be interesting to see how she does part B, right? Because at part B, she will now have, let's see, 1, 2, 3, 4 of the things. And then she'll be looking for acceleration. So it might be a little bit harder to pick an equation there. So I'll be watching out for that. But I really liked the way that she did that up. Now here, it's interesting. She started to drop the vector sign. She's talked about it, right? She's like, well, we don't know. She said we don't know much about direction, but I think what she meant is that it's in one direction, like just slowing down. So very cool.
Let's start by writing out that equation without doing anything to it. Displacement equals 1/2 initial velocity plus final velocity times time.
Cool.
This equation is also true.
And now that I think about it, that's exactly the equation I used to make my guess. Because I was thinking, so the average speed, which is about 5 meters per second, has to be the average between 2.8 and something. That's why I said, 6 or 7 or 8 meters per second.
Even if we only have magnitudes. So I can kind of ignore the vector symbols for this problem.
Cool.
Now, this problem doesn't have the variable we're solving for on the left-hand side of the equal sign. So let's rearrange some variables and solve for the unknown first, before plugging any numbers in.
Oh, I like that.
I'll start by multiplying both sides by 2.
So I'll just pause here. So often when I'm finding these videos, I'm not 100% sure what level it is. All I know is that this one says honors physics at the top of it. But I feel like I learn a lot about the audience at this point, right? Because a whole bunch of us might do a bunch of these algebraic steps in one shot. There's some of us who would do, okay, multiply by 2, right? So there's even a step in between here and here. I remember in 6th grade, you had to write whatever law that was obeying. It's like the associative law or something. And I got sick and tired of that. But it's really fascinating to watch how many steps are talked about, how many steps are done. And there's this really interesting balance because some students are like, oh yeah, we're done. This problem's done. The rest is algebra. But there's other students who are like, I have no idea how to do this. So I think you always have to strike this balance. And of course you have to know your audience. And of course she does, right? We're just taking some guesses. She knows what her audience needs here from an algebraic support mechanism. So I just really am intrigued by that process. Is this early in the semester? Is this late in the semester? Has she taught this a whole bunch and already knows exactly how much algebraic help that her students needs? Does she know that she's leaving some behind and knows that she's going to have to do, a one-on-one with them or really help them out? All of these things are unsaid. We talk about the hidden curriculum all the time. At the college level, it's like, oh, did you realize you had to sign up for that course? The hidden curriculum. And to me, these hidden steps, these hidden teaching steps, these hidden decisions, I think are really, really fascinating.
Then I'll divide both sides by time.
Oh, okay. Okay, so that's interesting. She didn't write it out. She's like adding it all in one step. She didn't cross out the T's, though, so that's fascinating. Okay, but then she rewrote it.
And lastly, I'll subtract the final velocity from both sides of the equation.
I wonder if she's going to do VI plus VF minus VI on the right-hand side, or if she's just going to write VF.
Now we have an equation where the variable we're looking for is on one side all by itself.
Yeah, now plug and shove.
So that means I can plug some numbers in.
So here's the fascinating thing, right? If you compare this to the very first equation she wrote down, the very first equation made me think average and had me kind of work it out. Honestly, this equation, I have no intuition here. I would literally need to plug the numbers in to get an answer. So it's fascinating that to get it algebraically, you have to land here, but that intuition step was actually at the beginning. Oh, it's the average. Oh, okay, I need a number who, when averaged with 2.8, gives me roughly 5. Right? I mean, so I was able to get orders of magnitude. I know that it's bigger than 2.8, and I know that it's bigger than 5 actually, and I'm guessing it's less than about 10. Yet here we have to actually plug in. So that's really interesting if you compare and contrast the intuition steps versus the algebraic steps.
So V initial, what we're looking for is 2 times the displacement, and once again, that displacement is equal to 40 meters.
So 80 divided by 8 is, 9.
Divided by the time.
Minus 2.8 is about 6.2.
Minus that final velocity. 2.8 meters per second. Plug all that into your calculator. And you should find that the initial speed is 6.61 meters per second.
Cool. I love all these.
And we stop and ask ourselves, is that reasonable?
Decibels.
Is it reasonable that a truck would be going 6.61 meters per second? That's absolutely reasonable. If you think about a truck moving and how big 6 meters is, that seems pretty darn reasonable.
It's like 20 miles an hour or something like that.
So that's our answer to part A.
Cool.
And then we have part B.
Yeah, so I wanted to see how she does this.
Part B says,
question mark.
Find the magnitude of its acceleration.
Because now we have everything but.
So now we're looking for something different. We're looking for acceleration in part B.
Well, that's cool. You hit extend page and it gets longer.
Once again, magnitude only. We really don't know anything about direction, so we can't do anything with that. So we know 4 out of the 5 variables, and the 5th one is the one that we're looking for. That means we have all kinds of options as far as which of these equations to choose to find acceleration.
So that's so cool. So what she was saying is now it's not a matter of really, finding the exact right one, because before she was saying, well, let's figure out which one is not at all involved. And in part A, this was not at all involved, so this is your target for sure. Now she's saying, my God, we know everything but A. We could use this one, it's got an A in it. We could use this one, it's got an A in it. And we could use this one, it's got an A in it. Any of them will work because we know everything else. And it's so interesting when you think about the scaffolding for students. Students sometimes, this is too much information. They're like, am I supposed to do all three? Which one is the right one? So I'm really curious to see how she makes her decision. What would I do? I would do this one. Why? I don't know, it seems the easiest. Tangling out A from this one, I guess is about as easy as this one, but I don't have to square the time. Here I have to square the velocities. I'm just thinking about like how many buttons on the calculator. So I'm thinking I would do this one. Let's see what she does.
Choose the easiest one. Why bother making it harder on yourself? In my opinion, the easiest one is that very first one.
Boom.
The one that says that the final velocity equals the initial velocity plus acceleration times time. The funny part is, that's actually just the definition or the equation of acceleration rewritten. I'll show you what I mean by that.
That's a great point.
V final equals V initial plus acceleration times time. To isolate A, I'll first start by subtracting V initial.
Okay, here isolating A. Man, to me it's a one-stepper, right? And so I'm like, oh, she's going to do it all again. But again, she knows her students. She knows, I could just immediately write VF minus VI over T. But she knows her students. She knows that this, what she's about to write down, is vital to not lose them. My question for all of you is, you've got a few students who are like, yep, right? What do they do? Do they just, okay, do they fast forward? Do they pay attention because they might have missed something? Are they checking those other two equations? What do you encourage them to do? That's what I would do. I would say, hey, if this algebra is going too slow for you, can you do me a favor? Can you check that those other two equations give us the same answer? But there's some students, right, who are like totally lost, don't know what you're doing yet, and they need to see this next step, the scaffolding that we're building in early on.
From both sides. And then I'll divide both sides by time. So that means that acceleration is V final minus V initial over time. Well, final minus initial is really the same thing as saying delta V over time.
That's cool. That's cool. Connecting
and that's our equation for acceleration that we learned.
Connecting to an old point. Yeah, that's very cool.
Now that I've isolated acceleration, I can plug some numbers in.
6.6 minus 2.8, just a little under 4.
V final, we know already, that's 2.8 meters per second.
What did I say?
The initial velocity we just calculated, 6.61 meters per second.
It'd be about 1 meters per second squared.
And we're given the time to be 8.5 seconds.
Oh yeah, that's going to be negative. Forget about that.
Now, when I'm plugging this into my calculator,
right? What she's about to say, I'm guessing, is that, this is going to be negative. Right? Yeah. Right? The students need to reflect on those negative signs and figure out why they end up being negative. You heard what I did I don't know if you heard me say it, but I did the opposite. I did 6.6 minus 2.8 is about 4 something. You know what I mean? And so I think that it's fascinating to write out and say, oh my gosh, we're getting a negative sign here. And it's really, really important to say, well, we're slowing down.
Instead of plugging in that 6.61, I use the answer that's already on my calculator, either by scrolling up to it and hitting enter or by inputting answer into my calculator. So when it comes out, my answer ends up being more exact rather than using the 6.61.
That's cool.
We're allowed to do that since it's a calculated rather than a measured value.
We are allowed to do that.
What I end up with is a negative 0.448.
Yeah, so like
per second squared.
0.05
Now
Gs.
we have to stop at the end and think if our answer makes sense. If I look back at the problem, I see that the problem said find the magnitude of its acceleration.
Very cool.
Magnitudes cannot be negative. Therefore,
I'm just going to stop right there. It seems like she's at a closing point. Lots of really cool stuff in here. I love the algebraic scaffolding. I'm really intrigued by the vector idea. And she even said it. She said, well, we won't need to use the vector versions of these equations. So that's, I thought, was really, really cool. And these checks, these gut checks that she's doing, I think are really, really interesting too. So really, really great job. All right, everybody, have a great day. And remember, physics teachers are awesome.